All right, let's say that this same 15 kilogram mass is sitting up at the top of a 5-meter ledge. Okay? Yes, sir? Sure you can. Sitting up at the top of a 5-meter ledge. And we said that before that we used, work equals force times displacement times cosine theta. You know what? If you're always pushing up to lift things and gravity's always pushing down, what would you say about this cosine theta? Isn't the theta always going to be 0 if I'm just lifting stuff upwards? You're always lifting up and your displacement's always up. Let's just make this be 1, okay? Because they're always going to be in the same direction. So every time I lift something, that cosine theta is going to just reduce down to 1 anyway. So people say, well, really this force applied, if you're lifting things, is equal but opposite. Well, equal in magnitude, though, to mass times acceleration due to gravity every time I lift something. And then the displacement stays the same. And it's really displacement, if I want to get really specific about it, displacement in the y direction. So every single time I lift something, the work it takes to lift it, or the work that I have to give it, is going to be that object's mass times acceleration due to gravity times the displacement from some 0 height that I lifted it. And so they said, you know, like, if this happens over and over again every time I lift something, and we recognize that that's what we call gravitational potential energy, why don't we just make it simpler for ourselves and say gravitational potential energy is equal to an object's mass times acceleration due to gravity times the height above some 0 baseline, some 0 height, that I lift that object. So we come up with a new formula. We call it the gravitational potential energy formula. And it's on your equation sheets that you got at the beginning of the semester. But gravitational potential energy, easy to calculate. So gravitational potential energy is MAD, or MAGD if you throw in all the subscripts. So we've got our gravitational potential energy. Having said that, let's quickly, just very quickly, calculate the gravitational potential energy again. I know we did it once before with the same scenario. But let's just get it all written out. 15 kilograms times 9.81 meters per second squared times 5.00 meters. And we get a gravitational potential energy at that 5-meter height of, was it 735.75? Yep.
What's the second one?
This one right here or this one here?
That one.
Work equals mass times acceleration due to gravity times displacement in the y direction. Because really, when you lift something, you're just displacing it in the y direction. And the force that you're using to lift it is equal but opposite to the force due to gravity. Okay, so we've got a gravitational potential energy up at the top there. What did we, actually let's even call it position 1. So that's EG1. Remember once upon a time we also said that we could talk about what EK1 is if it's just sitting still at the top? What's EK1 up at the top? If it's just sitting still?
0.
Yeah, 0 joules. And so just a second ago, we also said, well, if it falls off the edge, we can talk about at position, well, some later position, what its kinetic energy is. You know what? I also want to talk about its energy part way down. So I'm going to call this position 3. I'm trying to think in advance here. And this is position 2. So I could say that at position 3, and I'll just write it down here, at position 3, Eg at position 3 is equal to, what was it? If it's at a height of 0, what's its gravitational potential energy? 0 joules. EK3, what's EK3 equal to?
EG1.
Yeah, same as EG1, all got converted into kinetic energy. So 735.75 joules. Now something maybe a little bit more interesting happens in between at position 2. So here's position 1, here's the information for position 3. At position 2, let's say that you get to a position at position 2 where the gravitational potential energy is 367.85 joules. Is there anybody that can tell me how much kinetic energy you have there and how you get it? How do you think you can figure out how much kinetic energy there must be there? I'll give you a hint. Energy can't be created or destroyed. So this guy here has to come from somewhere. How much energy do I have to start with? Got to be same amount as Eg1. How much energy have I lost from my original Eg1? Looks like this amount, right? So I could even say minus Eg2. You know what? I don't even like using this as Eg1 because that seems a little bit, well, maybe confusing. Let's call it the total energy at position 1. Because maybe there could have been kinetic energy at the beginning as well as gravitational potential energy. There could have been. There wasn't this time, but there could have been. So forget about Eg1. Let's make that into a total. Total energy 1, capital T. So total energy at position 1 is 735.75 joules. And the gravitational potential energy at position 2 is 367.85 joules. How many joules is wrapped up in kinetic energy at position 2? Anybody done the math already? I chose a really specific position. Yep.
367.9.
Yeah, but 367 point, actually it ends up being about 8.5 if I were to carry off these decimal places a little bit further, but 0.9 joules. If this is how much kinetic energy I have at this point, and this is how much gravitational potential energy I have at this point, about how far down do you think I am in my fall?
Halfway.
About halfway down. Turns out exactly halfway down. I mean, forgiving a little bit of rounding errors there. Exactly halfway down. So at exactly halfway down, what's my height going to be? 2.5 meters. Yep. And, you know, we could go back. We could confirm that. You want to know how we confirm that we actually are at 2.5 meters? We could take a look at our Eg2. And we could say, hey, look, Eg2 is equal to mass times acceleration due to gravity times delta dy at position 2. And I can confirm that position 2, or height 2, or delta dy2 is equal to 2.5 meters. Just have to isolate for delta dy2 and plug in my values. And I can say delta dy2 is equal to Eg2 divided by mass times acceleration due to gravity. Eg2 we said was 367.85 joules. Mass was 15 kilograms. Acceleration to gravity, as always, is 9.81 meters per second squared. And do I get about 2.5? You do the calculations. There may be a few trailing decimals there, but you get about 2.5 meters. And I can confirm that 2.5 meters really is my height if that's my gravitational potential energy. Yes, ma'am?
So how did you get the gravitational potential of 367?
Oh, now that was one that I just gave you as a given.
Oh, okay.
Yeah, that's fair enough.
Like in a question, no, give us that.
Yeah, I would give you that. Or I would say, hey, look, you're at 2.5 meters up. Now you calculate gravitational potential energy using this equation, and then you tell me how much kinetic energy I have left over. Okay? So I could work that problem in both directions.